Hello there, Mr. Sutton here, bringing you the BC Calculus 712 Part 1 homework solutions on the limit comparison test. On this problem, we're trying to figure out whether or not this series converges or diverges. So there's no real good test to get this one immediately. However, it looks kind of geometric, so we can try comparing it to the geometric series 1 over 2 to the n, or 1/2 raised to the nth power. So we'll compare it to this series. Now this series here has a common ratio of 1/2, an absolute value of that. It's geometric, common ratio of 1/2. Since that's less than 1, we know this is going to converge. So we just have to figure out which comparison test to use. Now right here, this denominator is smaller than the comparison series, which means overall this is a larger fraction than what we have here. So that's the wrong way if we want to use direct comparison. However, limit comparison would work on this. So we'll start by verifying that this function and this function are both greater than 0. So I'll say this function greater than 0 and this one also greater than 0, but we have to pick an n value that actually makes that true. If I plug in 1 for n, this will all come out positive, so that's good. And now I just have to take the limit as n approaches infinity of my original series divided by my comparison series. There we are. We'll do a little same change flip here to simplify this fraction. So I have 2 to the n over 2 to the n minus 1, again as n approaches infinity. And I'll store this in L, whatever this comes out to. So as n approaches infinity, I can forget about this little minus 1 here. We really just have 2 to the n over 2 to the n, which I can reduce to 1. Since I end up with a limit that is a finite positive number, an L value between 0 and infinity, that means that since my comparison series converged, my original is also going to converge by the limit comparison test. On this problem, I'm trying to figure out whether or not this series converges. So this one's not really good for nth term test or ratio test or any of those, but I can compare it to the series n over n squared. Whenever I see a rational function, I'm thinking a comparison test. So it's kind of similar to this one, which reduces to 1 over n. Now 1 over n you might recognize is the harmonic series, which we know diverges. So if I want to show that this series then behaves like the harmonic series, I have to use a comparison test, either direct or limit comparison. Taking a look at this fraction here, it looks like the numerator is going to be bigger, but so is the denominator, which is going to make it hard to tell whether or not overall this is less than or greater than the harmonic series. Since I have that ambiguity, I'm going to go with limit comparison on this one. So let me verify that the original and the harmonic are both greater than 0. So this is definitely going to be greater than 0 for all n values 1 and greater. And also the harmonic series. So we'll say that's true for n greater than or equal to 1. Let me set up my limit now. So I'll let L equal the limit as n approaches infinity of original series over harmonic series, or whatever the comparison series is. Same change flip this thing. I've got n times 2n plus 1 in the numerator. And denominator, we just have n plus 1 quantity squared times the invisible 1 there. So now as n approaches infinity, I can forget about this little plus 1 down here. It's really just n squared. I can also forget about this plus 1 up here. I have 2n squared in the numerator. So overall, that comes out to 2. Since the limit is a finite positive number between 0 and infinity, in other words, that means that since my comparison series diverges, my original series also diverges by limit comparison. On this problem, I want to know if this series converges absolutely, conditionally, or not at all. We'll start by testing for absolute convergence by basically forgetting about this alternating part. So I'm just going to consider 1 over 1 plus radical n. Now this looks very similar to the series 1 over radical n, probably behaves like that series. So let me just compare this to 1 over root n, which is a p-series with a p-value of 1/2. Since that's less than or equal to 1, we know that this comparison series is going to diverge by the p-series test. So now, can we do direct or limit comparison on this? Well, if I'm adding 1 to the denominator, that makes this a smaller overall fraction. If you have something that's smaller than a series that diverges, that doesn't really tell you much of use. So we're going to have to use limit comparison instead. So let me start by verifying that I have two positive series. We have this first series is greater than 0, and so is this second one, and that's actually going to be true for n greater than or equal to 1. There's nothing that's going to make this negative. So now let me take my limit as n approaches infinity of the original series divided by my comparison series. Now we'll do a little same change flip. We've got radical n over 1 plus radical n. And as n approaches infinity, we can forget about this little 1 down here. It's just root n over itself, basically, which comes out to a limit of 1. Since that limit, L, is a positive finite number, it's between 0 and infinity is how I show that. That means that since the comparison series diverged, this original here must also diverge by limit comparison. But this isn't the original, it's just the absolute value version of the original. So let me just write absolute value diverges by limit comparison. But I'm not done with the problem. Just because the absolute value version of this doesn't work doesn't mean the alternating version won't work. So let's look at our alternating version. It is, well, big surprise here, alternating. And since the denominator is growing and the numerator really isn't, this is also decreasing in absolute value to 0. Since our original terms are alternating and decreasing in abs value to 0, that means that this is going to converge by the alternating series test. And it's going to converge conditionally because it only converges with alternating thrown in. On this problem, I want to know which of these series diverges, so you got to be careful here. They're asking about diverging. So we have to test each of these individually. Let's start with the first one, and I'm going to need some room, so let me just section off all the space up here for this first one. Okay, so this one looks very similar to the series 1 over k squared, so we're going to compare it to that series. Now 1 over k squared, you might remember, is a p-series with a p-value of 2. Since that's greater than 1, this comparison series converges. So we're going to see if we can prove that this expression behaves the same way. So to do it with comparison, if we try direct comparison, it's not going to work out so well because although we have a larger denominator, we also have a larger numerator, so it's kind of ambiguous whether or not one of these is bigger than the other. So we're going to use limit comparison instead. So I verify that this expression here is positive, and so is my comparison series, and that's going to be true for all k values greater than or equal to 1, but we can say 3 just to be on the safe side if we really wanted to. And I'll say k, not n. Since we've met the conditions of the limit comparison test, let's go ahead and use it. So I have the limit as n approaches, or k actually approaches infinity, of this is going to be the original series over the comparison series, 1 over k squared. Same change flip to simplify the fraction. We've got 2k squared in the numerator and k squared plus 1 downstairs. As k approaches infinity, this plus 1 becomes insignificant and we can forget about it. So we just have 2k squared over k squared, which is just 2. And since this limit is a finite positive number, between 0 and infinity in other words, that means that this series here is going to behave the same way as 1 over k squared. It's going to converge by the limit comparison test. All right, so it doesn't diverge, which means that anything with 1 in it has to be eliminated. So the only thing that we can eliminate off that is choice D. Well, let's take a look at the next two series now. Option 2 here, this is a geometric series. The absolute value of the common ratio is 6 over 7. That's a number less than 1. By the geometric series test, then, this is going to converge. So anything with 2 in it can be eliminated. So that would be B and E. So it's really down to C converging or diverging. C is an alternating series. These terms alternate, and since the denominator is growing, our terms are also decreasing in absolute value to 0. Since this is actually, and you could even go better on this one, this is actually just the alternating harmonic series. So we automatically then know that this is going to converge, which means nothing diverged, trick question, so that's going to be choice A. On this problem, we're trying to figure out which of these three series converges, and it could be more than one of them. So let's take them one at a time and give it a try. For this first series, I have a combination of exponentials and factorials. The nth term on this one, if you take the limit as n approaches infinity, is going to go to 0, so we need to do a little bit more. Ratio test is usually a good one when you have exponentials and factorials, so let me try that out. Let me take the limit as n approaches infinity of the n plus 1th term, that's 8 to the n plus 1 over n plus 1 factorial, and that's going to be over the nth term, 8 to the n over n factorial. Same change flip to simplify our fraction, so we've got 8 to the n plus 1 times n factorial in the numerator. In the denominator, we have n plus 1 factorial and 8 to the n. Simplifying this now, these 8's can cancel out by subtracting the exponents, so that leaves us with just an 8 in the numerator out of those. And then with these factorials, n plus 1 factorial is really n plus 1 times n factorial. So the n factorial gets canceled out. We just have an n plus 1 downstairs. So to recap, upstairs we had an 8, downstairs n plus 1. As n approaches infinity, this is going to be a bottom-heavy term, a bottom-heavy fraction, so this whole thing is going to 0. And since 0 is less than 1, our ratio test unambiguously tells us that this series is going to converge. All right, on to the next one. So for this next one, it's tempting to do the ratio test on this one as well. However, if you look closely here, if you take the limit as n approaches infinity, you'll notice that we have a top-heavy function here. Factorial growth destroys polynomial growth. So this goes to infinity. Since that's not 0, this diverges by the nth term test. And then for this next one, we're going to use a comparison here. Whenever you have all these pluses involved with a polynomial, comparison test is a good way to go. So let's compare this to n over n to the third power. Now this reduces to 1 over n squared, which is a p-series with a p-value of 2. Since that's greater than 1, this is going to converge by the p-series test. So now which comparison test are we going to use? We haven't actually committed yet. Direct comparison is not going to work so well on this one because both the numerator and denominator are greater than this original function here. So it's kind of unclear whether the overall fraction is going to be bigger or smaller than what we started with, or at least within our comparison series. So instead we're going to use limit comparison. I have to verify first that these are both positive functions, and they are. This function here is positive. This function here, the 1 over n squared, is also positive, and that's going to be true for n values of 1 or greater. So now, using our limit comparison test, we have the limit as n approaches infinity of the original series, this big series up here, divided by the comparison series 1 over n squared. Using same change flip to simplify this fraction, we've got n plus 1 times n squared in the numerator. Denominator, we have all this craziness with an invisible 1. And now, if we just take a look at the degrees here, upstairs we have basically n cubed. Downstairs we also have n to the third if we multiply all this out. Those are the dominant terms. So n to the third over n to the third just comes out to 1. Now, since this number is a finite positive number, since this L that we just found is between 0 and infinity, that means that since our comparison series converged, our original series also converges by the limit comparison test. All of which means that we've got convergence at 1 and 3 for our options, so that's going to give us choice D. On this problem, we're asked which of the following series can be used with limit comparison to determine if this series here converges or diverges. So in general, with limit comparison, you want to pick a comparison series that has the same degree as the original, so that it's easy to take the limit of the ratio of those two things. So a good series to use would be n squared over n cubed. Of course, that's none of the answer choices, but we can reduce this. So this reduces to 1 over n, the harmonic series, which is one of our answer choices, choice A. On this problem, we want the interval of convergence for this series. Since this is not geometric, we need to use the ratio test to get this started. So let me take the limit as n approaches infinity of absolute value of n plus 1th version of this, so x minus 3 to the n plus 1 over 2 parentheses n plus 1, over nth term for this thing, so just what you see here inside sigma. Now let's do a little same change flip. So we've got x minus 3 to the n plus 1 and 2n in the numerator. Denominator, we've got the other two things, 2 parentheses n plus 1 and x minus 3 to the n. Now let's reduce as much as we can here. These x minus 3's can reduce by subtracting the exponents. So that just leaves us with x minus 3 to the first power in the numerator. And we still have a 2n up there. In the denominator, we still have 2 parentheses n plus 1 or 2n plus 2, however you want to write that out. And now as n approaches infinity, this little plus 1 in here is going away. So you essentially have a 2n over a 2n, which cancels, leaving us with just x minus 3 in the absolute value. To get my interval of convergence, or at least get the rough draft of it, I'm going to set this less than 1. And then I can rewrite without the absolute value as -1 less than x minus 3 less than positive 1. Adding 3 to all three sides to get x isolated, we have 2 less than x less than 4. Question mark, because we need to test the endpoints since we got this from the ratio test. So if x equals 2, let's test this first endpoint here. What happens to the original series? Well, 2 minus 3 is -1, so this is -1 to the n over 2n. This is a series that alternates, and since our denominator is growing, this is going to go to 0 in absolute value. So our terms are alternating, decreasing in absolute value to 0. Therefore, this series converges by the alternating series test. Now let's test the other endpoint, 4. At x equals 4, what does our series look like? So 4 minus 3 is 1. 1 to the n is just 1. So this is all 1 over 2n. So we've got 1 over 2n for that series. Now, one way you could deal with this would be to compare this to 1 over n, the harmonic series, and probably have to use the limit comparison test on this one. But an easier way to do this would just be to factor a 1/2 outside the series, like so. And now what's left inside the series is clearly the harmonic series, which we know diverges. So that's a very quick way of proving that this diverges without using limit comparison. So then our final interval of convergence, we're going to have 2 less than or equal to x less than 4.